Okay, so welcome back to the second part of our discussion on simple optimization techniques. Of course, if you haven't watched the first part, you should definitely do that before continuing with the rest of this video. In the last lesson, I outlined a number of steps that you can actually use to solve a simple optimization problem like this one. But then at the end of the last lesson, I promised to actually show you an example where I used this technique to solve an actual problem. And now it's time for you to see that problem and to see exactly how we'd go about solving it. Okay, so for the example I want to give you, I want you to imagine that you're in charge of designing a can to hold 330 mils of soda. Okay, so suppose we wanted to minimize the amount of money we spend on each individual can. Well, to do that, the first step is going to be to identify the parameters that we're working with. Since we're dealing with a cylindrical can, we can change the radius and the height of the can. Okay, so now that we have our parameters, the next thing we want to do is to find our target. And as we said, we want to minimize the cost of this can. Okay, so it is perfectly possible to minimize the cost of the can. But instead, what we're going to think about is the fact that the can is made of metal, and the cost of the can is mainly made up of the amount of metal we use to build the can. So instead of setting the target to be the cost, how about we instead try to minimize the amount of metal we use to build this can? Well, to do that, we're going to want to minimize the surface area of the can. Okay, so saying that we want to minimize the surface area isn't really enough. What we're going to need to do is to actually find the function that describes the target in terms of the parameters we've chosen. Since our parameters are r and h, what we want to do is to find the surface area in terms of r and h. Okay, so to just make this clear, we want the surface area to be some function t of r and h. Okay, so it's perfectly possible to actually find this function t directly. Now to do that, we're going to want to actually find the surface area. So the surface area of the top lid is going to just be pi r squared, and then the bottom is also going to be pi r squared, so we have 2 pi r squared. Now once we've found the top and bottom area, we also want to find the area of this outer wall over here, and we can actually do that by finding the circumference and multiplying it by the height. Now the circumference of this can is just going to be 2 pi r, and the height is just going to be h, so the surface area is going to be 2 pi r h. Okay, so now we've actually found our target, but it's in terms of two variables, the radius and the height. But this is actually a very useful criteria we can use to evaluate basically any can, because if you just give me the radius and the height of the can, I can tell you exactly how much surface area and therefore how much cost you're going to incur to actually produce it. Now to make this really clear, I'm actually going to draw it on a graph. Okay, so I've just gone ahead and drawn this particular function for a number of different surface areas. So this one over here indicates all of the possible shapes where the surface area is 50 centimeters squared. And this one over here indicates all the shapes where the surface area is 500 centimeters squared. Now I want you to understand that different points on this graph indicate different shapes for your can. Okay, so I've drawn on a few examples just to clarify this. If you have a really small radius but a really large height, then you get this really narrow and very tall can. If on the other hand you choose a very large radius but a very small height, then you get something that resembles a canister. And if you balance the two out, you'd get a shape that looks a little bit more like this. Now, if you just wanted to minimize the surface area of your can with no regard to anything else, you just pick a really tiny radius and a really tiny height, right? The trouble with this, of course, is there's no way it will hold 330 mils. And this brings us to our next point. We need to actually identify our constraints, and our constraint is that we need to hold 330 mils of liquid. Now, just to be clear, these units over here represent centimeters. And a milliliter is the exact same thing as a centimeter cubed. So therefore we can state our constraint by saying 330 centimeters cubed is the same thing as our volume. Now since we're working in centimeters all the time, I didn't bother to write the units on. But to find the volume of a can like this, we just have to find the area of the top and multiply by the height. So that's just going to be pi r squared times the height. Okay, so now step 3 over here is actually done. We have our constraint in terms of our parameters. Here it is right here. We know that pi r squared h has to be the same thing as 330. Now it also helps to actually draw on the constraint onto our graph. Okay, so to be clear, all of the cans along this line over here are actually going to hold exactly 330 mils. If you're over here, you hold less than 330 mils, and if you're on this side, you hold more than 330 mils. So what we'd like to do is we'd like to follow this curve and find the point on it that has the minimum amount of surface area. Now we can already see that the surface area over here gets really large, so we're not going to expect a can with a shape like this. If the graph was drawn really accurately as well, you'd also notice that the surface area grows as you make the height larger as well. So it looks like the sweet spot is going to be somewhere around here. But to actually find it, we're going to need to combine this and this over here. And this is actually our fourth step. We need to use our constraint and substitute it into the surface area somehow. And now we actually have two choices. We can either solve for the radius, or we can solve for the height. In general, you can always choose to do one or the other, but one of them is usually going to be easier. You have to be careful because picking the wrong one can lead to way more work than you probably want to do. In general, I like to avoid square roots, so I'm actually going to solve for h and make it the subject instead. Now doing that is really easy. I'm just going to divide both sides by pi r squared. Now once you know the height in terms of the radius, it's actually possible to substitute this into the surface area anywhere you see a height. This is going to remove every instance of the h in the surface area formula. Now before we go any further, it's a good idea to simplify this expression. So I'm going to cross this with this, and then I'm going to multiply the 2 and the 330 to get 660. Okay, so now as you can see, we have the surface area in terms of just the radius. There's no h in this formula at all. One thing I always like to do is to visualize things, so let's go ahead and actually graph this function on a new axis. Okay, so this clearly has the behavior we were expecting. You notice that the surface area goes down and then it goes back up, so there is actually an optimum point right here. Now to actually find this optimal point, we just have to set the derivative of ds on dr equal to 0, so that the slope is 0. But to actually do that, we're going to need to differentiate this function first. Okay, so to differentiate this, remember we just write this as r to the power of minus 1, and then we just use the bring the power down rule to get this. Okay, and now we're finally ready to actually set the derivative equal to 0. So let's go ahead and do that, and then we'll simplify. To begin with, I'm going to multiply everything by r squared. That's going to have the effect of actually cancelling out this term and turning this one into an r cubed. And then finally, all we have to do is to solve for r. Okay, so once everything is said and done, we can see that r is exactly equal to the cube root of 660 divided by 4 pi. We can find out what this is approximately equal to with a calculator. Okay, so we can see that this minimum point over here occurs exactly when r equals 3.74. We can find the surface area of our resulting can by putting 3.74 into the surface area formula that we found. I'll do this in my calculator again. Okay, so we can see that I just replaced every r for 3.74. And when I plug this into my calculator, I get 264.35. Okay, so if we were actually interested in the shape of the can, we should find the height as well. And we can do that with this formula over here. If we just sub in 3.74 for the radius again, we will find the height. Okay, so it looks like the optimal height would be 7.5 centimeters. And this actually gives us a very interesting shape for a can. Now I want you to remember that the diameter of the can is just twice the radius. And if you look at this, it looks like twice our radius is approximately equal to our height. That means our optimal can is actually shaped something like a square when you look at it from the front. Now of course, real soda cans don't look like this. So did the people designing them just not realize that they could make a more efficient can? Well, not quite. It turns out that if you were designing a real soda can, you wouldn't just be optimizing for its surface area. You'd be considering other factors like its strength, or other things as well. Now don't get me wrong, there are actually problems that are useful to solve with a single variable like this, but there aren't really that many of them. But this technique is actually really important, because as you learn more and more mathematics, you'll realize that to solve more complicated problems, we're just going to generalize this technique over here. So I hope you can see how this weird technique over here can be used to optimize all kinds of strange things. And now with this, we've actually completed our example. Okay, so in this lesson, we talked about optimization. And we said optimization was all about finding the best version of some parameter. We identified that anytime you're going to optimize something, you want to look for the parameters, the target, and a constraint. Now, of course, real optimization problems may have more than one target and potentially more than one constraint, and it can have lots and lots of parameters if you like. But for these really simple problems, you're generally looking for exactly two parameters, and that's always going to be the first thing you want to do. After that, you want to find a function that actually describes your target. Now the target is just the thing that you're trying to optimize. But in order to actually optimize it, you're also going to need to find yourself a constraint, like this one over here. Once you've found a useful constraint, you can turn your problem into a one-dimensional problem. And then once you've done that, you can solve for the maximums and minimums on that one-dimensional problem. Now, as we said, optimization is incredibly useful, and so many people use it on a daily basis. Now, the general techniques of optimization are a little bit more complicated, but they are built on these exact same principles. Now, I hope this simple introduction to optimization has whet your appetite a little bit and hopefully got you excited about the subject. But in the future, I hope you're going to actually see some of the more interesting and much more useful applications of optimization. And now I'd like to end there. We've actually completed our discussion on simple optimization.